Alright guys, so you just learned about refraction and what causes refraction. Namely, there's a difference in speed as a wave travels from one medium or from one type of material to another. And so what we're going to talk about in this video is the mathematics behind that. In other words, how can we calculate what the angle of incidence and the angle of refraction is? And the short answer is that we use Snell's law to do this. So I'm going to tell you about Snell's law. It's very straightforward, very simple to use, and I think you'll like it. So let's say we have a surface, and on this side of the surface the wave moves fast, and on this side of the surface the wave moves slow. And as you should know, that we measure these angles relative to this normal line. So if we have a wave coming in right here in the fast, and then it's going to bend towards this line. Okay, and on this line, let's say this angle is theta 1, and on this side, we'll say it's theta 2. So I want to make note that we keep on measuring these angles relative to this normal line. Okay, so it's not between the ray and the surface. It's between the ray and this normal line. So we have theta 1 and we have theta 2. And in order to understand Snell's law, you have to know about something called the index of refraction. So index of refraction. So the index of refraction it's related to the speed of a wave, and the way we define the index of refraction n is that it's equal to the speed of light c divided by the speed of light in the material. So c is 2.998 times 10 to the 8th meters per second, and this is the speed of light in a vacuum, and it's pretty close to what the speed of light is in air as well. This v right here is the speed of light in the material. Okay, so if we're going to calculate the index of refraction, then that's going to be related to the speed of light in the material. So you can see that if light goes much slower in a material than it does in the vacuum, then n will be much greater than 1. In fact, n will be greater than 1 for anything that has light traveling through it more slowly than it does in a vacuum. Okay, so again, this n is our index of refraction. Alright, so with the index of refraction now, we can use this and we can write down Snell's law. So Snell's law simply says that if you take the index of refraction of material 1, say it's up here, times the sine of theta 1, this is called the angle of incidence, then that has to be equal to n2, the index of refraction of this material down here, times the sine of theta 2, or the angle of refraction. So I told you guys it was simple. So yes, a simple little law. Make sure you guys get that in your notes, and this is called Snell's law. And so you can imagine that we could use this, say if we know the two indices of refraction, we could calculate, and maybe the angle of incidence, we can calculate the angle that light will be refracted as it travels from air into the medium, or from one medium to another medium. We could also, however, use this, if we can calculate the index of refraction, we can also use this as a way to calculate the speed of light in a material. And so that's what we will look at in the first problem here. So looking at this first problem, we have a beam of light that travels in the air and it strikes material. And you are given the angles of incidence and refraction. Incidence is 63 degrees, refraction is 47 degrees, and you are asked to obtain the speed of light in the material. So why don't you guys have a go at it and see what you can get. Alright, and we are back, and here's the solution of the problem. So as always, we want to draw a picture. This is physics class after all, so we draw a picture and we draw a nice little normal line. And we have our incoming light, we have our light being refracted, we have our angle of incidence, the 63, our angle of refraction of 47. And so we set up Snell's law. Again, the angle of refraction for air, because again, the speed of light in air is really close to what it is in the vacuum, we just assume that the index of refraction for air is going to be 1. And so since this is 1, we do some algebra, we solve for n2, and we get that n2 is equal to 1.218. So then we can take our definition of the index of refraction and we can solve for this v2. This will be the speed of light in the material, and solving for v2 gives us 2.46 times 10 to the 8th meters per second. So it is slower than it was in the vacuum, and I hope you got it right. Alright, so on this slide we have a discussion of something called the critical angle. Okay, so I'll write that up here for you. So if you need software issues, if you need a title for the slide, let's call this critical angle. Okay, so what is this critical angle and why do we have to worry about it? Well, this is for a situation where instead of having light travel from fast to slow, we have light traveling from a slow to a fast. And as it does that, you can imagine that this angle, now this theta 2 will be the angle of incidence, so this theta 2 will actually be smaller than what theta 1 is. Okay, so theta 1 will always be greater than theta 2. You can imagine that as theta 2 increases this way, theta 1 will increase this way until eventually theta 1 will be 90 degrees. It's going to be parallel to the surface. And when theta 1 is 90 degrees, what's going to happen is instead of this light exiting the material, it's actually just going to bounce back. It's going to be reflected back, and this is called internal reflection. Okay, so that's what this is referring to. And so this angle theta 2 that makes this happen is called the critical angle. And so what we want to do is we want to get an expression for this critical angle, this angle that theta 2 has to have to cause the reflection rather than have it be transmitted and refracted out. So we go back to Snell's law. Again, this occurs when theta 1 is 90, so we'll just plug in 90 degrees here, which means sine of 90 is 1. And n1 equals n2 times sine theta c, and then solving for theta c gives us this equation. So this equation right here is what we will use to calculate the critical angle for a substance. Notice that the greater n2 is, the smaller this angle is. Okay, so if you have something like that has a very high index of refraction like a diamond, okay, you'll get a lot of internal reflection, which is, well, you know, why diamonds are cut the way they are, and it makes them sparkle. Okay, so on to our next problem with that. So in this problem, we're going to use this idea of a critical angle in order to find out what the index of refraction of a solid actually is. Okay, so say that we don't know what the speed of light is in a certain solid, and yet we still want to know what, nor do we necessarily know what the angle of incidence is, but we still want to know what the index of refraction is. So this is what this problem is asking you to solve for. It's giving you this critical angle, and so use this along with the equation that we just talked about in the last slide, and see if you can figure out what the index of refraction of the solid is. Alright, and here's the solution. So we set up our equation for critical angle, and because we want the index of refraction, we'll take the sine of both sides, which gives us this equation over here. We plug in our critical angle value that we're given. We solve for index of refraction, and we get 1.54. So I hope all this made sense to you. If you guys have any questions, just let me know in class tomorrow.